All right. I don't know if that's focused. Number 11. We're continuing the assignment 3-2 here. We'll see if my camera wants to focus or not. I want to graph that. And so when you have absolute value bars like this, we're actually going to first graph without the bars and then adjust it after that. Let's see if I can make it happen. Oh, it is what it is. All right. So if you graph this without, what are some of the things I'm looking at when I do that? And so before I go any further, I start with some pre-calculus work. And so I can factor out an x. That's x squared, take away 3. Let me look here for a second. So right away, I know that there's an x-intercept at 0. If I take x squared, take away 3, and make it equal to 0 and solve it, then my other x-intercepts are at positive and negative root 3, so almost 2. So those are my x-intercepts. My y-intercept is 0 when I plug in 0. And the last thing would be the end behavior. And so the power term is x cubed, so I know it goes up to the right and down to the left. So this is my pre-calculus knowledge. The calculus part is to take the derivative and see the turning points increasing and decreasing. Again, I'm going to make it equal to 0. You can divide by 3. You can factor. Difference of squares. The answer is positive and negative 1. And then you plug into here and understanding the multiplicity makes this much easier. So a negative times a negative is positive, and then because of the odd exponents, the sign changes at each one. If it had an even exponent, the sign would stay the same. This tells me at negative 1 is a maximum, and at positive 1 is a minimum. So if I plug negative 1 into here, it's negative 1 plus 3. That's 2. That's a max. The minimum, plug in positive 1, and 1 take away 3 is negative 2. So again, we're going to graph this, having an understanding before we do the absolute value bars. Again, take the derivative, 6x, make it equal to 0. So 0 is a critical number. A negative number makes it negative, and a positive makes it positive. So that's a point of inflection at 0. So 0, 0, which is an intercept, is a point of inflection. And then I put it all together, and then I'll make an adjustment. So here, I'm going to first graph g at x without the bars. And so at negative 1 and 2, at positive 1 and 2, we have point of inflection. We also have intercepts that are right here and here. That's negative root 3 and positive root 3. And then you can connect and understand. So it's concave down, and then it's concave up. Goes up to the right and down to the left. Now, what adjustment happens when I have the absolute value bars here? So what's going to stay the same, what's going to change? And so anything on the axes is going to stay, and anything above is going to stay. But this point below is going to be reflected up. So it's going to be at positive 1, positive 2. And again, the intercept stays the same. And so this now has been reflected up. So this is what it looks like. And there you go. All right, number 12. True or false? True or false? If the derivative is positive, then the limit as x approaches infinity is infinity, and then show an illustration to your answer. So first of all, that's false. It doesn't have to be true. So let me give you an example of where that wouldn't be true. So it says, if the derivative is greater than 0, so this means that it's increasing. Can you have an increasing function where the right end doesn't go to infinity? That's what it's asking for. And if we have a horizontal asymptote, I'll just do it with this. if I have a horizontal asymptote, this can be increasing but not go to infinity. So here is an increasing function that goes to a number. In this case, it could go to 2. That's not going to infinity. So 12 is false. You can have an increasing function that doesn't go to infinity, that goes to a number. Number 13. Discontinuities. So these are all review questions. They're really powerful to pay attention to review questions so you don't forget. The discontinuities come from the denominator, so I'm going to factor the denominator. That's -1 and -2. So we have a discontinuity at x equals +1, and it's non-removable. That means it doesn't cross out. And at x equals +2, it's removable. Now, what does it mean that it's removable? It creates a hole, right, and you can remove it. A good review there. 14. It's a piecewise. So each piece I look at, each piece is continuous by itself. So the only thing I look at is where the piece breaks off. So if I plug 0 to the top and 0 to the bottom, at x equals 0, there's a jump. And a jump is non-removable. And the idea of a limit is that the limit doesn't exist at a jump. So something is non-removable if the limit does not exist. If the limit exists, it's removable. Number 15. Oh, this is an old friend. So this is a step function or greatest integer function. So at every integer, there's a jump. So at every multiple of 3, and a jump is non-removable. See if I can spell. There it is. So at every multiple of 3, there's a non-removable discontinuity. So every multiple of 3 when you divide by 3 is an integer, which creates a jump. 16, can you evaluate a limit without your calculator? Step 1 to evaluate a limit is to plug in what the number is. So if I evaluate at 2, be careful, it's indeterminate. So that means I don't know yet. So I'm going to factor and see if something's removable. So that's a difference of squares. Remove. When you remove, the number left over is 1. Now plug 2 in, and you get the answer. So the limit does exist after you remove the discontinuity. Number 17. 17? Yeah. The limit as x approaches 2. If I plug 2 in here, it's an important difference between 16 and 17. If you plug 2 in, it is not indeterminate. So if I plug 2 in here, it's 4 over 0. That means this limit doesn't exist. It's indeterminate when it's 0 over 0, or infinity over infinity, but that's a different question. Here, it's 4 over 0. That's what makes it, makes the limit that doesn't exist. Number 18 is an end behavior question when it approaches infinity. That has to do with the power terms. When the power term on the bottom is more powerful, then it's going to 0. Number 19, find an equation, and it says you may use a calculator, so I like that idea. Oh, I need my calculator. 1 second. It's being charged. I'm still here, I promise. I'm still here. It's not good for the video, right? To like step away from the video. But I'm here. Number 19. We have y equals 4 to the exponent x minus 2. And I need to find a tangent line. So these are the 3 things I need to know. So x equals 5. Y, when I plug in 5, 4 cubed is 64. And then the slope is found by doing the derivative. So we're just going to use our calculator directly. So ultimately, I'm finding the derivative at 5. That's what's going to give me the slope. So menu calculus, derivative at a point, and then I type it in. The value's at 5. And then I type it in, 4 to the exponent x subtract 2. Control enter. I get 88.72. Just checking the answer key to make sure I'm on track. Yeah. So you don't need to round. So it's 88.722. And then put it together. It's y equals the slope, 88.722. And then x minus 5 plus 64. Number 20. Find the points at which the graph has horizontal tangents. The word tangent means derivative. So let's do that to begin with. Derivative. Make sure you do it implicitly correctly. So take the derivative, do it implicitly. Next, get y prime by itself. So I'm going to factor out y prime here. That's 4 and 4y. I'm going to subtract 2x, and then I'm going to divide. I can simplify it too, but it's unnecessary. Horizontal tangent is when it's equal to 0, because the slope of a horizontal line is 0. So make that the numerator equal to 0, and it says find the points. So the x value is 0, so I'm going to come back here. I'm going to plug in 0 for x. I still need to find the y value that goes with that. So I need to solve that. So I plugged in 0 for x, and I want to solve for y. This is a quadratic equation. So I have 2y squared 4y minus 6 equals 0. Divide by 2. And then you can factor it and solve it. So it's positive 3 and negative 1. So the two answers for y are negative 3 and 1. So what are the points where there are horizontal tangent? So x is 0 and negative 3, x is 0 and positive 1. So those are the y coordinates that go with the x coordinates. So putting these together, and you have your 2 points. Horizontal tangent. Tangent means derivative. Derivative means slope. The slope of a horizontal line is 0. That's the connection. All right, 21. Oh, I'm not done 20. 20b, that was A. So in B it says, determine whether each of these points is a local minimum or maximum, and do a second derivative test. And so I need to know the second derivative. So let me write down the first derivative again. Negative 2x over 4 plus 4y. So because I'm going to reduce it down, divide everything by 2, just to make it a little simpler. So the second derivative then would be the bottom times the derivative of the top minus the top times the derivative of the bottom, and then the bottom squared. Now, we know the derivative at that point is horizontal. That means the derivative is 0. So when I plug in the point, and the point is 0, and the first point was 0, negative 3. I want to know if the answer is positive or negative. So this is 2 plus 2y. So if I plug in negative 3, that's a negative times a negative, which is positive. So if I plug in negative 3, 2 times negative 3 is negative 6. 2 take away 6 is negative 4, and a negative times a negative is positive. If I plug in 0, this is just 0, and if you square something, it's positive. So in other words, it's a positive over a positive. So because it's positive, it's concave up. 0, negative 3 is a relative minimum because it's that way. If I use the second point, which is 0 and 1, if I plug 1 in here, 2 times 1 is 2. Plus 2 is 4 times negative 1. So this is negative, this is 0, and this is positive. So it's a negative divided by a positive. So that means it's concave down, which creates a maximum. That's using the second derivative test, using concavity to know if it's a maximum or a minimum. 21. We just did this. It says find. So we need the first derivative again. I'm not redoing the derivative. It's the same exact equation. So the first derivative is negative 2x, 4 plus 4y, or I should have really write down the reduced form. And it says vertical tangents. So break down the word vertical tangent. So the word tangent means derivative. So that's what I'm looking at. Vertical means the slope is undefined. So this is slope. Where is it undefined is looking at the denominator equal to 0, different than horizontal, and then solving it. So when y is negative 1, it is undefined. And then I go back to the equation, and I plug in negative 1 and find what the x value is because it asks for the point. So I go back into the equation, plug negative 1 in for y, and solve it. Now, this is going to be positive and negative root 8. So at positive and negative root 8 and negative 1, these 2 points, we have vertical tangents, or the slope is undefined. 22. In number 22, you're given a bunch of information. So first of all, it says h at x, this is for a, h at x equals f at x times g at x, and we're supposed to find the derivative at 4. So this is the product rule. Can you do the product rule in its generic form? So the first times the derivative of the second plus the second times the derivative of the first, and then can you plug in 4 wherever there's an x, and then you look at the question, and f at 4 is 2, g prime at 4 is 5, you're just plugging in the values, g at 4 is 3, and f prime at 4 is negative 1. So from the question, this is where the values come from. So 10 take away 3, and the answer is 7. For B, J, you don't see J very often for a function. Fun. So step 1 is to take the derivative here, generically. This is the chain rule. So 3 times 1 in front, write down the base over again, subtract 1 to the exponent, and then the hook, which is the derivative of what's inside. Now plug in 4. And then plug in the values from the question. So f at 4 is 2. F prime at 4 is negative 1. So this is 12 times negative 1, so that's negative 12. 23. Oh man, it's a good one. It has a lot of parts to it. So let's do this. Such an important question to not whatever it. So try to do your best here. This is a great review question on velocity, acceleration, position, and we need to do this review. And it says you may use a calculator for this. So what is the object's velocity equation? I don't need a calculator for that. That's the derivative. B, what's the initial velocity? Plug in 0, and the answer is negative 1. Now, units, it's seconds and centimeters. So that's centimeters per second. Now, what that means is initially the object is moving left, is what's the negative means. C, what's the object's acceleration? So take the derivative, and it's 12t minus 6. What's the object's acceleration at 3? So plug 3 in, and that's 36, take away 6. Now the unit would be centimeters per second squared. Can't even say that out loud. So getting the units correctly for acceleration, or centimeters per second. What's the object's speed at 1? So it's the absolute value of the velocity. So if I plug 1 into the velocity, I get 6 take away 6, 0 take away 1. So the absolute value of -1 makes it +1 centimeters per second. F, let's see if I have room here still. When is the object moving left? So take the velocity equal to 0. I'm going to use my calculator to solve it because I'm not in the mood to to factor that. I'm not even sure if it's factorable. So we're going to go menu, algebra, and solve. And then we take the velocity equal to 0. There it is, equal to 0, comma t. And so, there's two answers there. So that's -0.145. Let me do a number line here. So -0.145 and 1.145. And then I plug into the velocity. So pick a nice friendly number like -1. So -1 gives you 6 -1. That's 6 plus 6, right? That's a positive answer. And then the signs are going to change. You plug in 0 and then plug in a positive number bigger than that. And then the question is, when is it moving left? Is that right? So from -0.145 to 1.145, it's going to the left. G, what is the object's displacement? So displacement has to do with the position, and it's just where it starts and where it ends. So from 0 to 2 seconds, you plug in 2, and then you plug in 0, and you subtract. You can use your calculator. I'll just tell you the answer. When you plug in 2 and plug in 0 and subtract, you get the answer 2, and it's centimeters. Where are we at? H. What is the object's total distance between 0 and 2 seconds? So between 0 and 2 seconds, the object changes direction here. So I need to use that number and set it up twice. And it's always a positive number. And then you add that up. So what's the position at 1.145 and at 0? I'm going to tell you, I'll show you here with the calculator, that really there are so many parts to this question that the smartest thing to do at the beginning would have been to define it in your calculator. To go into your calculator and define it. And so I'm going to take away what I have here. You're going to have to use X. And not t, but that's okay. And so put that equation in there, which is 2x cubed subtract 3x squared. Silly me. So 2x cubed, move the cursor, subtract 3x squared, subtract x plus 8. Now that you press enter and it's in your calculator, come back here, and then you can plug in those values. So it's F1. So it's F1 at 0. So here, if you typed it in completely, you go press this button here. So the button beside the 9, and get the absolute value button. And then type in what we just did. So F1 at 1.145, subtract F1 at 0 plus absolute value bars. And now it's F1 at 2, subtract F1 at 1.145, and then you have your answer. Oop. So 6.151. and that's in centimeters. So total distance, you have to think if the object changed directions, and you want to know the distance it went in the one direction and the distance it went in the other direction. It's all positive numbers you add up, and there's total distance. Number 10, we're on G. This is H, I. When is the object decreasing? So velocity is decreasing when the acceleration is negative. So again, the acceleration is 12t, subtract 6, make it equal to 0. And so t is a half when it's equal to 0. And then plug in to know when it's negative. So the velocity is decreasing when the acceleration is negative. So if I plug in 0, it's negative, and if I plug in like 10, it's positive. So from negative infinity to 1/2, the velocity is decreasing, and that means the same as the acceleration's negative. J, when is the object's speed decreasing? So speed means I need two number lines. So one number line for velocity. So we already had that number line. That's negative, I'll do it over here again, negative 0.145 and 1.145. And it went positive, negative, positive. For acceleration, we just have 0.5 or a half. I'll write it as 0.5 so you can compare them. And then when do the signs match? So when is the speed decreasing? Sorry, when the signs are different. So when the speed is decreasing, the signs are different. So from negative infinity to negative 1.145, it's positive and negative. After that, the signs match. When do the signs not match again? And so from 1.145 to, no. Is that the only time they don't match? So from here to here, the signs match, and then that's it. I think it's just that one where the signs don't match. No, from 0.5, so it's from 0.5 to 1.15. So we have a negative and a positive. So from 0.5 to 1.145, that this is positive and this is negative up to there. So there are two moments where the signs are different, and that's when the speed is decreasing. The speed is increasing when the signs match for velocity and acceleration. All right, 24, 5, 6, 7. Let's look at it. Can you match the graph to the appropriate derivative in terms of what we're looking at? So if I look here, the derivative here is where it's increasing and decreasing. So where's the turning point at 0? And it's below and then above. So do you see a below and then above? And that at 0 is a turning point. So 24 matches with B. 25. So again, I'm looking for turning points. We have no turning points, and it's only increasing. So everything is above for the derivative, which is the only one where everything is above with no turning points. Now, here at 0, the slope is 0. So the slope is 0 and everything is above. So 25 matches with C. A is also above, but it doesn't show that at 0, the slope is 0. So here, the slope is always 1. That's different. So 25 matches with C. 26, the slope of this line is positive 1 and it never changes. So the derivative is at positive 1 and never changes. So 26 matches with A. And then 27, well, 27 obviously must match with D. But like, why does it? So the turning point there is here. See how the turning point, which is in between 0 and negative 1, that's the x-intercept. The other turning point between 0 and 1 is the other x-intercept. Increasing means above. Decreasing means below. Increasing means above. And this matches that. So 27 matches with D. And then the last question, number 28. can you estimate slope off a graph? Or can you find it? So what's the slope here? So find it. So at A and B are both on the line with the same slope. Go down 2 and to the right 3. So A, the slope is negative 2 over 3, and B has the same slope because it's on the same line. C is on a horizontal line. A point on a horizontal line, the slope is 0. D is on a vertical line. The slope of a vertical line is undefined. E is approximately negative 1. If you drew a little tangent line, it's like down 1 to the right, just estimating it. It's definitely negative, right? F, if you look at F, it's a horizontal line. That's 0. At turning point, the slope is 0. G, positive 1, approximately, if you draw a little tangent line. H, here, this is a steeper one, right, than the other one, so I would say like 2, maybe 3. I, it's negative, and it looks like more like negative 1 if I was going to estimate it. When we do slope fields, it's going to be important to do this. J is right kind of at that turning point, so I think it's like 0, and you did it. So be able to approximate slope with a little tangent line and think, is it positive, is it negative, is it 0, how steep is it? Kind of approximating. All right, I'm proud of you. You did all your work. Mr. G Math over and out. Until next time.